first I want to just introduce Brandon, who joined us here at University of Michigan after graduating from Harvey Mudd. He has been such an engaged student here in the University of Michigan and has been an outreach ambassador for the robotics department pretty much since the year you started here. So every year since you started, pretty much. So engaging just in our community, doing outreach, and just really helping others in the department. But in addition to that, he's been doing amazing research at this intersection of motion planning and human factors of trying to support inspection, which you'll get to hear about. And this diversity has also shown up in where he's publishing and where he's presenting, going to conferences and presenting at places like the Human Factors and Ergonomics Society, as well as IEEE Aerospace and IEEE Robotics conferences. So with that introduction, I'll turn it over to Brandon to share with us your research.
Awesome. Thank you so much. Hi, my name is Brandon, and today I will be studying my work on human-aware in-orbit space structure inspection planning. So let's start. So my dissertation work aims to support science that's enabled by spaceflight, where success has led to a cool burning flame that has aided engine design, satellite imagery of Earth that has aided weather prediction, disaster response, environmental health monitoring, microgravity experiments on drugs like Keytruda that has improved manufacturing and uniformity and ease of delivery. Finally, things like GPS, which everyone uses on their phones nowadays. All of these would not have been possible without spaceflight, which relies on space vehicles like the International Space Station or satellites like GPS satellites. So space vehicles that support these breakthroughs require inspection and maintenance because of the risk of micrometeoroid or orbital debris impacts, so hardware failure, and also just the isolated nature of space. Current inspection practices, including exterior cameras, line of sight through the windows, and manipulators, all have blind spots. You can see an example of that on the right. Shaded brown regions are blind spots. So inspection thoroughness actually requires spacewalks, which is a risk to astronaut safety. One way that NASA performs risk analysis is by ranking events by criticality. Criticality is a combination of probability and consequence scales. And you can see that the highest criticality events have the highest probability and highest consequence scale. But any of those events that are in the yellow or red squares are high priority. Spacewalk inspections for damage detection often show up in the bottom right-hand corner, low probability but high consequence events. But this risks astronaut safety. So we ask the question, can we mitigate these low probability and high consequence events using a space robot instead? So free-flying robotic inspection of the International Space Station can enable the inspection of these blind spots. But current approaches don't optimize for fuel consumption, information gain, or are limited to rendezvous docking scenarios. So generalized inspections for proximity operations require very complex collision avoidance constraints and are not quite this simple. We also shouldn't automate every part of the inspection. Perception algorithms for anomaly detection might propose spurious false positives shown on the left, or do not identify untrained edge cases where cables are identified as cracks on the right. So the segmentation test is not perfect, and identifying anomalies is even harder. So like astronaut spacewalks, we still need a human in the loop who will help identify anomalies. So this is my problem statement slide, and I'm making two key points. One, that the robotic space inspection of the space station can reduce astronaut risk. Also, that the system must integrate human supervision when possible for identifying anomalies. So how might we incorporate automation that optimizes for fuel consumption and information gain while also integrating a human in the loop to provide anomaly detection capabilities? So our approach begins by adapting a point-to-point planner from point-to-point robotic path planner to zero-gravity environments. And then we adapt terrestrial inspection algorithms to an in-orbit space station environment in a way that integrates these results from the point-to-point planner that we've already adapted. Finally, we integrate a human into the loop, or a system that will add a human into the loop for anomaly detection and perform evaluations on that system. So my work makes a couple assumptions. We assume that the inspector has perfect control, has perfect localization, and is a point mass, convenient. And we assume that all the obstacles are static and known. We also assume linearized coefficient wheelchair dynamics to describe the motion of the space robot. So this outline describes the structure of the rest of my presentation. I'll be coming back to this, but we'll start with the literature review of the gaps, starting with a focus on terrestrial inspection algorithms. So to answer this research question we posed earlier, we begin with our first gap. So I stated briefly earlier that there aren't any inspection planning algorithms for free flyers in space that maximize information gain, minimize fuel consumption, while also integrating a human into the loop. And so this gap reflects that that gap. I'll return to this slide, build out a flow chart that connects the research question to gaps, as well as aims, which correspond to chapters in my thesis. So the problem that we're focusing on is generating a trajectory with minimal fuel cost while also maximizing our inspection coverage. And this comes with two challenges. First is that each of these objectives is very nonlinear when considering occlusions, collision avoidance, and complex geometry, as well as robot dynamics. Secondly, these objectives directly compete with one another. If we reduce the fuel cost of a trajectory, we might have to sacrifice some inspection coverage. And if we increase the inspection coverage of a trajectory, we'll probably be sacrificing fuel consumption. So this leads to two classes of planner, one called a unified planner and the other being a decoupled planner. So unified planners optimize sensor coverage and traversal cost jointly. This operation is very high cost, and solutions are usually limited to a receding horizon planner, as you can see on the left, or a low dimensional or simplified planning space on the right. Both these unified and decoupled approaches somehow discretize the solution space, but when you decouple the problem and provide an optimal solution to each of the subproblems, we can provide a great balance between discretization and optimal solution potential. So this leads me to my first aim, which is adapting terrestrial inspection algorithms to space while accounting for orbital dynamics. So returning to the decoupled inspection problem, a generalization of this decoupled inspection problem first solves the set cover problem, which is a formulation of the viewpoint planning problem, then adapts the viewpoint, then solves for a cost minimal trajectory that visits all the viewpoints using the traveling salesman problem. However, this problem leads to a non-metric traveling salesman problem, and where we need to incorporate frictionless dynamics while avoiding obstacles. So optimal control can be used to find solutions to these complex space planning problems, but they often struggle to converge to a valid solution given that we have complex and non-convex obstacle fields. Sampling-based robotic path planners, on the other hand, like rapidly exploring random trees, also known as RRT, find solutions by expanding through the free space with collision-free edges to find a solution from a start configuration to a goal configuration. And this leads to our first sub-aim, aim 1A, which is adapting point-to-point robotic path planner to the space environment. Returning to this decoupled inspection planning slide, once we have our set of ordered viewpoints that the traveling salesman problem is going to give us, we have to perform one more step. In the case of terrestrial inspection, a quadcopter can follow a set of ordered viewpoints very easily because it's cheap to stop and hover and take a picture, for example. But when we move this into space, we have very high velocity nulling costs when we introduce orbital dynamics and just the frictionless nature of space. And so we have to process this set of ordered viewpoints into a feasible and fuel optimal trajectory. So we look to the optimal control literature and find that it can support an optimal control formulation, can support fuel consumption optimization, imposing control saturation constraints according to robot kinematics and thrust capabilities, collision-free motion that is guaranteed by safe region constraints. And so optimal control ends up being the best candidate for final trajectory generation, given that we have this structured problem where we have a set of ordered viewpoints that we can follow. This leads to aim 1B, which is designing this trajectory generation algorithm in a way that minimizes fuel cost, maximizes coverage, as well as avoiding collisions. I'll now move on to my second gap in the literature that focuses on human supervision of the automation. So earlier, we mentioned that human judgment in the inspection system is vital. So previous work actually showed that allowing a human to take over control, also known as human in the loop, increased or improved anomaly detection. However, in this previous work, participants did not prioritize fuel use, and the study didn't consider three-dimensional coverage and fuel optimized paths. So human in the loop design, especially in space, is very challenging for the following reasons. So since self-localizing in a 3D environment will have 6 degrees of freedom, 3 degrees of freedom in translation, 3 degrees of freedom in rotation, self-localization in space is very challenging. And on top of that, we add the influence of invisible orbital dynamics, and this task gets very, very hard, near impossible. So ensuring that the human operator maintains situation awareness throughout this whole inspection task is going to be very challenging. And this leads us to our second gap, which is that any algorithms that we adapt may not align with a human supervised application. And I'll populate this gap on the slide. So human studies also show that path curvature and vehicle heading influence an operator's ability to determine the goal state of an autonomous docking vehicle in space. We also know that fuel-efficient trajectories for proximity operations, especially in this inspection scenario, lead to paths that have many loops, as you can see on the right. And this has the possibility of disorienting the operator, since we're constantly changing orientation and looping around the space structure. So designing motion plans that support human operator situation awareness is really important and may influence the inspection performance. So this leads us to our second aim, which is investigating the influence of the motion plan as well as takeover modality presence on operator inspection performance for the inspection planner that we've created in aim 1. So this leads us to our first technical chapter, and this technical chapter will address aim 1A, adapting the point-to-point robotic path planner to the space environment. So this chapter and this aim led to 2 publications, one in IEEE Aerospace and one in AIAA, the Journal of Spacecraft and Rockets. So in this aim, we created a sampling-based planner for zero gravity that leveraged the RRT structure. This is the planner I mentioned before. Because moving in straight lines in space is very, very fuel efficient, we can swap the traditional concept of edges and nodes in the RRT tree structure to reduce the cumulative change in velocity heading. So this is also a first step in proximity operations, so we don't end up modeling any gravitational fields. We assume zero gravity. So in this tree, we retain the concept of a node-based tree, but allow nodes to represent straight line segments and edges to represent the intersections between them. But we need to randomly generate new lines that have a reasonable, which will intersect with the tree that we already have in order to expand it towards the goal state. So I'll show you how we do that. So first, let's say we have a tree on the right side, has 2 nodes, Qi and Qj. We begin by sampling a random configuration called x-plane and a random unit vector that will describe the plane that intersects x-plane. Next, we find all the intersections between this plane and the existing tree nodes. We then generate candidate nodes that connect these intersection points to that point on the plane, x-plane. We evaluate the cost it will take in terms of cumulative velocity heading change to get from the start node, x start, all the way to x plane through each intersection point. And then once we've found the candidate node that results in the lowest cumulative velocity heading change, we add it to the tree. And then we repeat this until we are able to sample the goal node and connect it into the tree. So we evaluated RRTZ by comparing it against RRT star and a modified version of RRT star called RRT star mod, which modifies the edge length limit and modifies the cost heuristic to the change in heading cost heuristic. After we compare it to RRT star and RRT star mod, we also take RRTZ trajectories and evaluate the fuel cost to follow these trajectories when in a gravity field. So this is an example of what RRTZ looks like when it's expanding from a start node 022 to a goal node 422 while avoiding obstacles. I've added dots to the end of each ray to visualize the intersections between the edges and the environmental constraints as well. And as you can see, the cost is slowly converging towards the optimal cost. To the end. So when we compared RRTZ against RRT star mod, we used 7 different environments and ran each algorithm on each environment. These are 4 of them. The remaining 3 were variants of case 3, which are just randomly scaled and rotated tetraedrons. These are the results of those simulations. We see that RRT star mod reduces the cumulative change in velocity heading cost, but it requires a long planning time to do so. RRTZ is able to reduce that cumulative change in velocity heading while also maintaining a low planning time. When we evaluated the fuel cost to follow RRTZ trajectories, we found that we can tune the velocity to result in a minimal fuel consumption. And as we moved away from the origin of our coordinate frame, or the target body in our space scenario, the cost of the fuel consumption also increases. We have a couple takeaways. RRTZ is able to generate low cost paths very quickly, but RRTZ only provides a path to follow. It doesn't provide the control inputs or how fast we should follow that path to yield the most efficient. We make 3 primary contributions. We flip the idea of nodes and lines from RRT to RRTZ. And in doing so, we frame the path search around this velocity heading change function. We also implement this geometric version of a proximity function. That was the node expansion I showed earlier, in order to expand these low-cost paths from a start point to a goal point. And then finally, we characterize the fuel consumption profiles of RRTZ and simulated proximity operations. Next, we'll move on to Chapter 2, Inspection Trajectory Generation, and this chapter corresponds with AIM 1B. This work also resulted in 1 publication in RAL, which I'll be presenting at ICRO this summer. So the inspection trajectory generation pipeline consists of 3 modules. First, a viewpoint planning module, then a viewpoint ordering module, and then trajectory generation. So the viewpoint planning module takes in a triangle mesh that describes the object that we're trying to inspect, and it yields a set of coverage viewpoints. The viewpoint ordering algorithm takes in that set of coverage viewpoints and yields an order to follow those coverage viewpoints. The trajectory generator formulates an optimal control problem to solve for a trajectory, which we're calling X, that is fuel and coverage optimized. First, in the viewpoint planning algorithm, we know that it's a well-studied topic in the literature, so we've borrowed triangle mesh-based pose generation and submodular maximization to solve for the viewpoint downsampling problem. Next, in the viewpoint ordering problem, we leverage the traveling salesman formulation or methodology, but we extend it to include orbital mechanics. Let me show you how we do that. So this is the same problem I mentioned earlier. So the orbital traveling salesman problem is non-metric and asymmetric because fuel consumed at between any two viewpoints depends on which viewpoint was traversed beforehand. So let A, B, C, and D be different viewpoints that we're trying to traverse between. We're trying to start at A, then go to B, and then end up at C somehow. But which viewpoint do we go through between B and C, E or D? And so according to the Euclidean metric cost, going through E is actually shorter than going through D. But it's also very expensive to go from B to E, given that we're coming from A, as compared to going to D, going from B to D, coming from A. And so we find that when we account for this velocity change in heading angle metric, it's actually cheaper to go through node D, even though the proximity or the total Euclidean distance is very similar. So our solution is to propose orbital traveling salesman problem solutions using the 2-opt method, and then evaluate solution quality based on this velocity heading change metric, and then choose improvements to existing solutions from the 2-opt method. So moving on to the final module, trajectory generation. In this module, we are able to generate a useful trajectory for the robot, which we're calling X, by optimizing an objective function f of x and u, which has two normalized terms that are weighted to control their influence on the solution. So the left term is our fuel consumption term, and the right term is our summed viewpoint proximity to the ordered set of coverage viewpoints. UIs are thrust at time step I, G0 is acceleration to gravity, ISP is the specific impulse of the cold gas thrusters that we're simulating on the inspection robot. NT is the number of time steps in our trajectory state vector, and N naught is the size of our coverage viewpoints set. So, and then YIX selects the closest state X hat to Q sub I in a range in a pre-specified range. F1 hat and F2 hat are just normalization factors that equally balance each of these terms when W is set to 0.5. So on the next slide, I'll show how we tune W. So we tune W by using a Pareto front. So let me explain this chart first. This chart shows each solution to the optimal control problem from a unique W. We've connected all the solutions that are optimal with respect to fuel cost or missed coverage, blue, and this is the Pareto front. And so once we have this Pareto front, we can choose a threshold for any one of these objectives to find the best solution or the most optimal solution with respect to the other, given that threshold. So in this case, we've chosen that we want at least 98% coverage. So we can choose the solution that gives us the least amount of fuel cost, given that we want 98% coverage, which is just below that line. So this is the result of one of these optimizations. The ordered viewpoints that we described before are the dots that are connected by dotted lines, and then the final solution is in black. From this work, we have a couple takeaways and contributions. First, that we have a traveling salesman problem formulation and trajectory generation that integrates linearized orbital dynamics in these gravity fields. We also provide this waypoint incentivized Pareto front solution selection that also optimizes fuel optimization, or also optimizes fuel and coverage. And we contribute an in-orbit space structure inspection pipeline, a traveling salesman extension that leverages RRTZ, and benchmark this against an impulsive viewpoint traversal optimization framework. That last point, something we didn't have time to include in this presentation, but is in the paper if you want to read more about it. So next I'll go over chapter 3, evaluating human automated teaming for supervised inspection. This chapter focuses on our second aim, where we integrate human in the loop and evaluate if motion path and takeover presence influences the inspection performance of that human. And this uses the adapted inspection algorithm that we formulated in aim 1. We don't have any current publications. We're still writing those up and submitting, so hang tight. In this chapter, we're aiming to answer the research question, how does motion plan and presence of a takeover modality influence operator inspection performance? To do this, we performed a human study. We had 40 participants. Those are the demographics, and we created inclusion criteria based on academic astronaut training program requirements from NASA, sufficient eye tracking ability, and also just the ability for someone to use the inspection interface. This research was done under this RB number as well. So to evaluate inspection performance, we first have to create a simulated inspection system, or a system that can simulate the inspection from a free-flying inspection robot that a participant can use. This is our inspection system. There's 2 monitors. The left monitor displays an egocentric view, which is a camera from the perspective or fixed to the inspection robot, showing from the forward direction. On the right screen, we have 4 third-person views that each illustrate what has and hasn't been seen on the left screen in green. There's a station model that gradually gets painted green according to what's seen on the left. On the right, we also have gauges that indicate station proximity, and velocity metrics, as well as 2 constraint gauges at the top, which I'll come back to later. Since we want to know the influence of the presence of a manual takeover modality on inspection performance, we modulated the presence of a rotation-only takeover modality. And the reason we're creating a rotation-only takeover modality is that if we give a participant full translational control, we also have to train them and how to control the robot in orbital proximity operations, which is very challenging. But it also leads to suboptimal fuel consumption, which coming from potential human errors or just the lack of an optimization plan. We constrained participants to 15 takeovers and a total of cumulative stationary takeover time of 3 minutes during these takeover scenarios. These constraints allow us to provide a proxy for fuel limitations in this scenario without actually having to teach them about orbital dynamics and how fuel is consumed in space. During takeover trials, the gauges shown in red appear. So during the study, participants must find and annotate anomalies on the screen with the mouse. And so you can see an example of an anomaly right here in the middle. And the anomalies appear on 3 different types of surfaces: divots, which are concave surfaces, edges, and faces. And then on the right, you can see an example of how someone annotates an anomaly. You can see the anomalies in a divot, and someone is moving their cursor over the anomaly and clicking. And the cursor becomes this orange circle. So during the study, participants inspected for anomalies from while the space robot followed an inspection path. This is the baseline inspection path. You'll notice that the baseline inspection path traverses across the whole station, switching from one module to the next very rapidly. And we thought this might lead to a little bit of disorientation, and it would also be very difficult to track for a participant what they've seen before and what they haven't seen before. And so we added a constraint called the local constraint, which inspects one module of the space station at a time. This allows participants to only need to think about one module at a time in terms of inspection. What have they inspected? What haven't they inspected? And then move on to the next. And so you can see, I'll isolate that trajectory per module in the next few slides. This is the segment that inspects the middle module. Then they inspect the module on the left, and then the spire module, and then the module on the right. In addition to these two paths, participants also have the opportunity to design their own trajectory. This is what we'll be calling the custom trajectory, the custom path condition, using this interface. So they're given a set of viewpoints, and they choose a subset of those viewpoints and order them into a set of ordered viewpoints. And as you might have guessed, we give this set of ordered viewpoints to the last module of our inspection pipeline, which optimizes for fuel and yields a final trajectory that they then perform an inspection using. So this is the overview of our study. We have two independent variables that will be modulating this rotation-only takeover modality presence, as well as the path condition, which includes the local constraint. We have 4 performance metrics. First is our anomaly detection rate. Then we'll be measuring the proportion of anomalies that a participant saw, given that that anomaly wasn't annotated. You can see an equation for that on the right. We'll also be tracking the surface coverage that a person inspects on the space station using these Toby glasses. We'll also be tracking the fuel consumption of each inspection. We have a couple of hypotheses for this study. First, that the local constraint and takeover ability will increase anomaly detection percentage, coverage percentage, and fuel consumption. We also hypothesize that anomaly detection percentage, coverage percentage, and fuel consumption will all have positive correlations. This is a little flow chart of our study. First, participants, so on the left, first participants put on the Toby glasses. Then they perform these 4 conditions, either the local constraint enabled or disabled, takeover modality enabled or disabled, and they're presented to the participant in a predetermined random order. Finally, the participant inspects using the takeover enabled custom trajectory, the one that they created. For the rest of this chapter, I'll be annotating the results using this color scheme, popping it up. So for data analysis, we first fit a binomial generalized linear mixed model to the anomaly detection data. And this allowed us to compute odds ratios that allow us to compare the outcomes between conditions. We also performed a Bruce-Pagan test of heteroskedasticity. I didn't practice that. We use this to assess the anomaly detection consistency with respect to fuel consumption. We also performed a bunch of z-tests with the Bonferroni correction. That one I did practice. It's also easier. We use this to compare the proportion of anomalies seen, given that they weren't annotated. This was the equation that I popped up beforehand. So these are our first results. So on the right, you can see each condition, the detection percentage of each condition. We further broke this down into the anomaly surface type that of focus. And on the left, you can see the odds ratio of each of these conditions relative to that condition on the bottom. And so what the odds ratios mean are, given that an anomaly was found during say on the top, the custom condition with takeover enabled, and it was on a divot, what is the likelihood that a participant found it compared to a face anomaly when a participant was using the local path with the takeover condition enabled? Next, I'll highlight a few results from this. First, without the local constraint, so all of the brown and orange bars, anomalies on the divots were the least detectable, closely followed by anomalies on edges, and then anomalies by faces, or on faces. Next, the local constraint supports divot and edge anomaly detection. You can see that green bars are further to the right than the brown bars, showing statistical significance on those odds ratios. And then finally, adding a takeover ability supports edge and face anomaly detection when the local constraint is also present. And from all of these results, we take away that the local constraint does successfully support anomaly detection across anomaly types. Next, I'm going to show you how anomaly detection percentage relates to fuel cost. So I'm going to populate this chart one condition at a time. First, you'll notice that all of these results are vertically aligned. That's because there's no takeover enabled. And so every fuel every fuel consumption metric for all of these trials is the same. Also, each dot represents one participant doing that condition once. We see the same thing for the local condition without takeover. All have the same fuel cost. When we introduce takeover, you see those fuel costs begin to spread out. But we also notice that this trend of decreasing variability as fuel consumption also increases. And we finally add in the custom condition, and we see this wedge shape. And so we use the Bruce-Pagan test to test the dependence of this variability on fuel cost. Find that there is a statistically significant a change in variability with respect to fuel cost. So these results show that there is a large variability in participant skill on the left, but also we can mitigate this influence of participant skill by adding the local constraint and by spending more fuel. Another takeaway is that some participants are able to achieve 100% anomaly detection in all of the trials, but this is very rare. These are the gaze surface coverage results, and we see that the local constraint, let me describe the graph. So on the left, you see gaze coverage percentage, and on the bottom, you can see our different conditions. And we see that the local constraint and takeover modality being present increase gaze coverage, or the percentage of the station that someone has looked at across a trial. So this graph on the right shows us that equation that I showed before. I'm popping back up. The percent or the proportion of anomalies seen given that a participant did not annotate them. And so we see that the local constraint leads to much lower proportion. Now this indicates that when the local constraint is not present, that people are looking at anomalies but not marking them. And so there are a number of reasons that this might happen. There might be a failure in cognitive focus, might be looking at an anomaly, but not actually focusing on it with their cognitive faculties. And so they don't recognize it. They might also recognize it, but maybe not realize that they haven't marked it before. Something gets lost in the mix. And maybe they did notice that they hadn't annotated it and they want to go annotate it, but they're not able to do so because maybe they need a takeover and they ran out of takeovers. So a few major takeaways from this research are that the local constraint does successfully support anomaly detection, but it comes at a cost of fuel consumption. But also, people just don't just mark any anomaly that they're looking at. This work also makes two major contributions. First, that we create this data set that enables investigation of the influence of motion plan, or investigation of motion plan trade-offs that consider human operator performance. And we also created a gaze analysis pipeline that allows us to map data that was captured by the Tobii eye tracker, so head-mounted data, to surface coverage in the simulation. This leads to my discussions and conclusions for my dissertation. So we found that RRTZ successfully adapts RRTs to zero gravity environments. We also created an inspection space station inspection planner that leverages RRTZ for the intermediate path generation, but it's also able to tune this decoupled fuel and coverage optimization using a Pareto front. Finally, we found that constraining paths to inspect one module at a time supported operator anomaly detection performance. This work has led to many avenues of future work. These are just a few. We plan on analyzing a bunch of more data from that human study that allow us to contextualize the results that we saw. There is also opportunity to adapt RRTZ to account for gravity fields. There's also opportunity to adapt the human-aware inspection trajectory generation to other applications on Earth that maybe such as quadcopter inspections or underwater ship hull inspections. We also found that there's there's a potential to investigate the effect of different variants of the local constraint on anomaly detection. We only explored one version of the local constraint being focusing one module to the next, but imagine that there are many others. So this is a full picture of my gaps and aims, all completed. Next, I'll move on to contributions. This is all of the contributions from all of my various chapters collected onto one slide for reference. Feel free to stare at that. Move on. Finally, my acknowledgements. I'd like to thank Professor Sterling and Professor Atkins for their continued and ongoing support throughout my whole PhD. I'm very grateful. Also, I'm thankful for the A2Sys lab and the Sterling lab for always being there to critique my presentations, offer me feedback. So thank you. I'd also like to thank all my friends who have been there to support me, literally, along the way. I couldn't have made it through without you guys. Also, I'd like to especially thank my partner Olivia and her family for supporting me as well. And finally, my family for always indulging me in playing football, catching, throwing, catching, and just being there as a supporting pillar. And finally, my grandfather, who could not be with us today, passed a year ago. And that concludes my presentation. Thank you very much.